Hi there. Thanks again for joining us. This is Space Nuts, a Q&A edition. This is where we answer audience questions. Well, we read them out and then we pretend we know what we're talking about, and most people fall for it. They might not fall for it today, though, because we've got some really interesting questions about a matter of matter that we cannot see. Does it matter? We will find out. Questions come up about gravitons. We're also going to answer a question about space telescopes. Now, that's right up Fred's alley. He knows everything there is to know about space telescopes. He's written books about these things, so this is going to be a good question. And a question has come up about whether or not Olympus Mons might make a good staging point for a space elevator. We will answer all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And it feels good to have his one and only self, Professor Fred Watson, astronomer at large, back in the chair. Hello, Fred.
Hello. Yeah, all ready to go, fresh and well slept.
Yeah,
sort of.
Yeah. I had a weird night last night. I actually went to sleep fast. I only woke up kind of once, which is a new world record, and then I woke up again at 5:18 a.m. and that was it. My body went, no, we're done. You can get up. Go and watch something on television because I'm not, I don't want to go to sleep ever again. So here we go. Who knows what'll happen tonight? Sleep is a weird thing. We need it, and yet our bodies sometimes refuse to comply.
Yeah, it is. It's bizarre. It's a strange thing.
Shall we answer some questions?
I thought that was it.
Well, I was just going to say, Fred, why can't I sleep?
Let's answer some questions, yes.
Okay. Our first one comes from Ben. He says, Ben here. It's good because I thought he was Ben too. The Aussie in Chicago with a few new questions. In your last question podcast, you mentioned about how 80% of matter is missing or not visible to us. And it made me think, how do we know or measure that amount in the first place? I know a lot of science is about measuring what we didn't find in results, but I'm curious about how they came to that 80% dark matter number. And secondly, for a smaller question, if you could pick the next large telescope to be launched, what would it be and why? I'd personally love to see a new, larger Hubble-type telescope with all the advances we've applied to it that we've learned from the James Webb Space Telescope. Thanks again for the great podcast. Thank you, Ben. Great to hear from you. Hope all is well in Chicago, home of the Bears, Chicago Bears. Right. So it's a matter of matter, and he's saying we know there's 80% of the universe made up of dark matter or thereabouts. How do we know that?
Actually the way that we get the accurate figures is quite interesting because it involves work of the kind that wasn't possible before astronomers started using fiber optics in their telescopes, and that's what I did. I was one of the pioneers of fiber optics in astronomy, and the systems that we built back in the 1980s, have now evolved into marvelous machines which are fully automated. The organization that I worked for has just delivered one to Chile, which will position 2,400 fibers in 57 seconds. And each one of those fibers can be aligned with a target star or galaxy, and that's the way you collect lots of information about very large numbers of galaxies and about their velocities, what we call their redshifts. So we'll get to that in a minute, because that's how we are so certain about these numbers, because of the ability to do that, to measure these very large numbers of galaxies, what we call large-scale surveys. But the story starts back in 1933 with Fritz Zwicky, the man who famously called some of his colleagues not just bastards, they were spherical bastards. The reason for that was that they were bastards whichever way you looked at them. That's why he called them spherical bastards.
That's very
so astronomers love him, yeah.
I'm sure they do.
I usually tone that down a bit and make it rat bags, but for this show, I can I could quote him verbatim.
It is a quote, therefore it's
a quote. Yeah,
it's a part of history.
It is indeed part of history. But what he was doing was measuring a cluster of galaxies, actually, in the Northern Hemisphere, constellation of Coma Berenices, the Coma cluster, a very rich cluster of galaxies. And he figured out that he was measuring the motions of all the galaxies. And when he looked at it, they were all going too fast for the gravity of what he could see to hold on to them. So if all that was there was what all he could see, then this cluster should have evaporated gazillions of years ago, and it hasn't. And he was the person who coined the term dark matter. He said there's something there that we can't see. The world of astronomy basically ignored it because it was just too hard to get your head around. There's obviously something wrong. We don't know what it is. We'll go and do something else. And it wasn't until, well, actually, there was an Australian who, in 1970, Ken Freeman down at the ANU, still a good friend, he figured out that galaxies were rotating too fast for what was in them to hold them together. And that, again, was largely ignored, that 1970 result, until Vera Rubin basically did the same thing, but worked out that in order for galaxies to stay together and not fly apart as they rotate, they must all be enveloped in a sort of sphere or halo, as we call it, of something we call dark matter. And that, in 1978, was the start of the modern era of dark matter. And so you can actually use those measurements to make a crude estimate of what's missing. You know, that you can say, use something called the virial theorem, which I haven't thought about for a long time, but that's what lets you weigh things by their motion. So you can weigh the dark matter by the motion of galaxies in a cluster, for example. You can then weigh what you can see, because you know roughly how much stars weigh, and the stars are what you can see, and the gas too. And then you can divide one by the other, and you do get this sort of 80-ish%. But the way that it's done today, as I've said, it involves these very large-scale surveys of galaxies and their positions and velocities in, you know, as much of the universe as you can see. Very, very large-scale surveys involving millions of galaxies. And when you do that, you can make statistical deductions that tell you that the universe is made of something like 70% dark energy, about 20% dark matter, about 5% normal matter, most of which is hydrogen. So that comes from the large-scale surveys. And it's because the positions of galaxies are actually determined by the gravitational forces that they feel. And, you know, that's the key to understanding dark matter and dark energy, to see how these forces stack up.
It's so hard to comprehend, because when you say that 5% of the universe is made up of stars, planets and gas, and you look out into space and see so many stars, so many other things, and yet you're only seeing 5% of what is out there, it's mind-blowing.
That's right. I mean, some of that figure of 5% is when you look at it as a fraction of the mass and energy budget. And energy and matter are, you know, they're interchangeable. E equals mc squared.
Yeah.
And so it's when you do that sum, you realise that, yes, 70% of the mass energy budget of the universe is dark energy. 20% is dark matter, 5% or thereabouts is normal matter. But most of that normal matter is invisible to us, because most of it is just cold hydrogen. The materials that make up the planets, in particular, the normal elements that we see around us on Earth, there's a vanishingly small fraction of that that represents, you know, their fraction within the universe.
Yeah. All right. So that covers his 80% question, but he asks a question about what will be the next large telescope to be launched. What would you like it to be?
Yeah, that's an interesting question. I mean, the thing that I'm looking forward to, and we'll see it online within the next probably 2 years, is the ELT, the Extremely Large Telescope down in Chile. That's going to be a visible light telescope with a mirror 39 meters in diameter, and it will be able to observe, because it's got this very sophisticated adaptive optics system that effectively puts it above the atmosphere. It will have 20 times the resolution of the Hubble telescope. So if you've thought the Hubble images that you see have fine detail in them, wait till you see what's going to come from the ELT, because it'll be 20 times better. And the reason why that's my favourite big telescope is that its cost has been almost since the beginning estimated at 1.3 billion euros, and it still is. It's on budget and pretty well on time. And remember, the James Webb telescope cost $10 billion to build, launch, and keep it going. As soon as you put things into space, their price tag goes up enormously, which is why I'm a big fan of ground-based astronomy, especially when we now have sites like Cerro Amazones in northern Chile, which is where the ELT will be, whose clarity and atmospheric stability you can hone with that adaptive optics system that the telescope's going to be fitted with. So that's what I'm looking out for next. I don't think you need to launch anything else into space to get anywhere near what the ELT will do.
Very exciting. Yeah. I heard they're going to have a visitors centre at the ELT, but the only thing on the menu will be BLT. So, sorry, I had to do that joke. It just, my brain doesn't let me stop sometimes.
No.
But, thank you, Ben, for the question. Great to hear from you. Let's talk about our sponsor, NordVPN. Now, if you care about your privacy online, maybe it's time to start thinking about a virtual private network, and NordVPN is by far the best you can get. It's one of the fastest and most trusted VPN services as well, helping you protect your personal data, secure your internet connection, and browse with peace of mind, whether you're at home or on public Wi-Fi. With just one click, NordVPN encrypts your traffic, hides your IP address, keeps your information safe from hackers, trackers, and snoopers. And you can also access content from around the world without restrictions, thanks to thousands of servers in over 60 countries. And as a listener of Space Nuts, you get an exclusive deal at nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free when you sign up. It's simple, it's fast, it's secure, it works. Go to nordvpn.com/spacenuts and take control of your internet experience today. That's nordvpn.com/spacenuts. Don't forget the code word spacenuts and their 30-day money-back guarantee.
Roger, you're loud and clear here also.
Space Nuts.
I'm going to do a bit of a switcheroo here because we're already talking about telescopes and we've got a question about telescopes, so we might just jump straight to that one. Hi, Fred and Andrew. Just wondering if Fred can shed some light, pun fully intended, on telescopes and the different types of light they can detect. I was recently thinking about how the James Webb Space Telescope uses mirrors to observe infrared light, but not visible light, while Hubble also uses mirrors for visible light, yet can't really see infrared. That got me wondering how mirrors, detectors and telescope design all come together, or don't, for different wavelengths. Could you please walk us through the various types of telescopes, optical, infrared, radio, all the way to gamma, and explain what kinds of light they detect, how they do it, and why each telescope can only be used in certain ways? Absolutely love the show. May you reign supreme for many years to come. Cheers, Ash. Thank you, Ash. And he just wants to know everything you've ever written down about telescopes, Fred.
Yeah, there's a book on it. I recommend Ash hunt it out. Yeah. It's called Stargazer, The Life and Times of the Telescope. It's the first big, thick book that I wrote. And it's still one of my favourites because even though it's slightly out of date, it opens by talking about what used to be called OWL, the Overwhelmingly Large Telescope, which was actually the precursor of the ELT we were just talking about there.
Right.
But when they were proposing OWL, which had an overwhelmingly large mirror of 100 meters in diameter. And then they realized it also had an overwhelmingly large price tag, which is why it came down to 39 meters. And that's fine, because that's still an extremely big telescope. Anyway, that's the plug over. That's the advert over. So basically, telescopes have sort of got the same ingredients no matter what they're observing. And that is something to gather the radiation, and whether that's very short wavelength radiation like gamma rays or long wavelength radiation like radio waves. You've got something to gather the radiation and either focus it in some way or at least concentrate it, and then something to detect it.
Yep.
And it's usually the detectors that are perhaps the most waveband critical, because you need different detectors, for example, to detect visible light from the ones that you would use to detect infrared light. And again, it depends on the infrared wavelength. So I guess starting right at the short wavelength end with gamma ray and X-ray detectors, they are almost the same sort of technology as are used in medical imaging. But to focus them, you've got to have very special technologies. My recollection of gamma ray telescopes, and things might have changed a little bit here, but they made mirrors which were called grazing incidence mirrors, which looked more like a piece of origami than a reflector that you'd imagine. But they did focus the light to provide that thing. And then you go to ultraviolet. The Hubble is sensitive to ultraviolet light, and for that it needed a very precise mirror. And we all know that the mirror was made very precisely, but to the wrong prescription. Exactly. For reasons that we haven't time to go into. So once again, the detector is sensitive to ultraviolet radiation. In fact, they've got quite wide band detectors. Hubble can detect long wavelength ultraviolet, whole of the visible, and also the short wavelength infrared, what we call the near infrared. And its mirror and detectors are capable of doing that. When you go up to the James Webb, you're right, that's tuned for infrared light. And that means your tolerances on the accuracy of the mirror are slightly less, because infrared light's got a longer wavelength. And, how accurate your mirror needs to be made is dependent on the wavelength. The longer the wavelength, the more relaxed you can be about the shape of the mirror. So a Webb telescope is slightly more relaxed, although still to very high tolerances. But the detectors are the thing that really render it not suitable for visible light. It's definitely got infrared sensitive detectors. It's also got a gold coating, and that's so that rather than an aluminium or silver coating like a visible light telescope would have, it's got a gold coating because gold reflects infrared light better. And then you get up to radio waves, and you're talking about often dishes, and a dish is just a big mirror, but one that's as I said before, it doesn't have to be as accurate as the mirror on a visible light telescope because the wavelength is longer, and that's why we see these much bigger telescopes for radio waves. You get the same sensitivity to detail with a bigger dish than you do with visible light. With a smaller dish, that's because that sensitive to detail is proportional to the wavelength. But the detectors are quite different in radio telescopes. They use often very sophisticated technologies where they're actually measuring the waveform itself, which you don't do with visible light, what are called heterodyne receivers and things of that sort. So that's walking through the various types of telescopes, as you've suggested, Ash. Is there another bit to the question? How they do it? Well, I've explained that. Why each telescope can only be used in certain ways. Yeah,
I guess the question he asks prompts a question in my mind, or a suggestion that you really could not build a single telescope that could do absolutely everything you'd want to do on all spectrums.
That's correct. There is a device which, in fact, is only used really in the microwave region of the spectrum, but it's called a bolometer. And a bolometer is something that is basically detects stuff, but it's insensitive to wavelengths. So in a sense, a perfect bolometer will be able to detect all wavelengths. Now, the reality is you can't do that, but that's the notion behind a bolometer. And what it means is that for microwave astronomy, the bolometer gives you a very wide range of wavelengths to cover.
So when you are planning to build a telescope, do you have an objective in mind before you build it, or do you build it and then think, well, what can we do with this?
No, it's definitely the other way around. You start off with a science case.
Yeah.
What are the questions that we really think are the most urgent questions to answer? And you've got things like, the nature of dark energy, the nature of dark matter. Are there any living organisms anywhere else in the universe? All the questions that you and I talk about on the show are the ones that scientists are still intrigued by. And there are many others as well. The details of the way galaxies interact with their environments. What about all these young galaxies that seem to be more mature than we think they should be at, when the universe is only a couple 100 million years old. Questions like that, they're all the ones that would go into the science case for a project. But there is always the background that you're going to find things out that you simply did not expect to find out. So that's usually added into the science case, the stuff that we just don't expect, serendipitous discovery. And there's been so many of those made by the world's great telescopes.
Yeah. Thank you, Ash. That's a great question, and I could tell Fred was excited about it. I'm going to go back to Ben's question about, what do you want the next big thing in telescopes to be? I've thought of one. I want to see the FWST. In Fred Watson Space Telescope. That's what I
like the sound of that. Yeah, I do too. I love the sound of that. Thank you.
Oh, well, you're a pioneer in fibre optics. I mean, it makes sense to me that you should have one named after you. Yeah.
I always think the reason for my hairstyle is because I worked in fibre optics, because the individual follicles got jealous of all these thin strands of material that I was playing with, and they all just fell out.
Yeah, they gave up. Yeah, they said, no, we can't beat that. See you later, Fred. We're going somewhere else. Thanks, Ash, for the question. This is Space Nuts with Andrew Dunkley and Professor Fred Watson, a Q&A edition. Let's tell you about our sponsor, Incogni. Now, if you've been overwhelmed by a barrage of spam calls and emails and targeted ads, robocalls, it's probably because they can find you online very, very easily and just harvest your contact information. If you've ever felt like that, then the answer is Incogni. What happens is data brokers collect and sell your details, leading to an endless array of spam and other potential risks. And if you want to get rid of that, Incogni is the answer. It's your personal data removal assistant. It automatically sends removal requests to over 210 data brokers, ensuring your information is taken down. You can even watch the progress of it through an online dashboard. With weekly updates, you can track the cleansing of your digital footprint. Plus, there's a 30-day money-back guarantee, so it's risk-free. It's called Incogni. Take control of your online presence. Visit incogni.com/spacenuts. And here's the kicker. 60% off if you use the code word spacenuts. That's incogni.com/spacenuts. 60% off if you use the code word spacenuts. Enjoy a peaceful online existence without digital disturbance.
Houston, Tranquility Base here. The Eagle has landed.
Space Nuts.
Our next question comes from somebody else. Hi, Fred and Andrew. Gravity is described by Einstein's theories as the bending of space-time in the presence of massive objects. Great. Why then does physics discuss the hypothetical graviton as a force carrier for gravity? What would a graviton look like were we to discover it or discover its existence? And why is it needed at all in the context of Einstein's theory? Thanks. Keep up the good work. Love the show. Russ from Stourbridge in the UK. Stourbridge?
Yep. It is, that's right. It's in the Midlands, Stourbridge, I think,
you are.
If I remember rightly.
Hi, Russ.
Time since I've been. Yeah, it's a good question. And that's kind of hard to know how to how to start it because there's so much to say. So, yes, general relativity, exactly as Ross says, is that space-time bends, or the theory says space-time bends when you've got matter there. And all the evidence is that general relativity is absolutely on the money. It's, it meets its predictions with such a high level of accuracy that it's almost mind-blowing. If I remember rightly, I think it's 1 part in 10 to the 18 or something like that it's been proven to work for. So that's great, but the physicists who look at the other end of the size scale, the ones who are interested in quantum mechanics and particle physics, subatomic particles, they say that all forces, and here we're talking about gravity in the Newtonian sense, that it's a force, have a particle that carries them. And so, we've got the photon for electromagnetic force, we've got the various force carriers for the strong and weak nuclear forces, and we've also got now the Higgs field, the Higgs boson. So what they're saying is that because gravity works that way, there should be a boson that carries gravity. And that's the idea of a hypothetical graviton. My suspicion as to how that links with relativity comes from the description of the Higgs boson that I think we might have talked about a few weeks ago. So the Higgs boson is, I think somebody asked about, how do you reconcile the Higgs boson with something that gives all the other forces their mass? Because that's what the boson does. And the bottom line is that what you're really talking about is the Higgs field, which is something like, they usually talk about syrup or molasses, and as the particles move through it, they get resistance because they're because they're in this sticky stuff, and that gives them the effect of mass. It's not an analogy that thrills me, I have to say, but it kind of gets the idea. And the only time the Higgs boson itself appears is when you've got something, a collision between particles. So the Higgs field is the main thing. But if you collide particles together, you get this thing that emerges from the Higgs field, which is called the Higgs boson, and that can be measured, which it was in 2012. And my guess is that the graviton, would be something like it. It would be a boson. It would emerge from the gravity field, and maybe would emerge when there were collisions in particle accelerators. But we have no evidence for it yet. So I think, Russ, I think that's the bottom line, that like the search for the Higgs boson, one day the search for the graviton will basically cough up the goods, and we'll understand it perhaps in a similar way to the way we understand the Higgs boson, that you need to actively create a boson from the Higgs field. So maybe you need to create a graviton from the gravity field, which we're used to talking about. And
some kind of particle to account for dark matter. And so,
well, that's right. Yes. Yeah. Well, dark matter would probably be a fermion, a thing that, is a matter particle rather than a force particle.
Okay. Gotcha. Fair enough. All right. So where does a light particle fit in? A photon?
That's the photon. Yeah, it's the gravitation. It's the electromagnetic particle. That's probably the best understood of the subatomic particles, because we use it all the time. Mm-hmm. We're using it as we speak.
Yeah, it's very handy.
It's very handy. Yeah,
I've found it quite useful recently.
Yeah. Good. You probably find the strong and weak nuclear forces quite useful as well, because they stop you falling to bits.
That's a good one. Yeah, keep that in mind.
Yeah, I think that's even more useful than photon, really.
The problem with all of this, Fred, is none of it gives me anything to work with to improve my golf game. So,
yeah, well, you've got to start with the notion that 5 irons don't float. And once you've got past that step, then...
We're getting some book plugs in today, aren't we?
Yeah, that's one for you.
Thank you very much. Thank you, Russ. I hope we covered that. I think we did. Not sure. But anyway, it's a work in progress. We'll call it that. Our final question today comes from Robert. He said, "Hi, my friends down under. I live in Akureyri, Iceland. And I'm very much looking forward to the eclipses this year in the western part of Iceland. However, your recent fabulous show regarding Olympus Mons on Mars, would this make a perfect candidate for a space elevator?" That comes from Robert. Hello, Robert. Thanks for sending your question in. Akureyri, you've been there.
I have, yes. I sent you some photographs so that you could see what it's like. We should put them up on the website.
We could post them on the Space Nuts podcast group.
That would be nice. Yeah,
all right.
There's a nice one of the main street, Marnie and me in the main street in Akureyri. We were there at this time last year, actually, Robert. So I'm sorry I didn't know you then, or else we'd have looked you up. But we had a great time there. It was part of our Iceland tour, which was not the best for weather, so we didn't see any aurora, but certainly experienced some really fabulous landscapes up in the northwest of Iceland. It was our first visit up to the northwest. We spent a lot of time in the south on previous trips, but Akureyri, such a stunning place, beautiful scenery.
They love their cathedrals, don't they, in Iceland? The churches.
Yeah.
Gee, they're amazing. The one we saw in Reykjavik just blew my mind.
That's right. That's the classic one. That is such an elegant building.
It is.
And indeed, the church in Akureyri is lovely as well.
It is. Yeah, you've got a photo of that one. I'll post that too.
Yeah. What was the question again?
Olympus Mons as a good platform for a space elevator.
Yes. There's a kind of problem because to make a space elevator stable, it has to start off from a point on the equator of whatever world you're trying to get up into space from.
Right.
And Olympus Mons, I'm told, is at latitude 18 degrees north. In fact, it's 18 degrees, 39 minutes north, which is not the equator of Mars. Yeah. So you'd have problems with it. It would need to stretch and shrink, and I think would probably shake itself to pieces. So I think you've got to have the equator. So that's a bit sad because Olympus Mons, as Robert is hinting at, is it's high enough that you kind of you're already out there. You're already on the way up your space elevator. So a nice idea, very nice idea, but I don't think it would work.
That's a pity. Oh, well, I suspect that the space elevator concept's probably not ever going to happen. It just sounds like it's too expensive, too hard, and there are easier ways to do things.
Yeah, well, that's right. Reusable boosters is the way to do it. And as we talked about in the last show, that's now basically the normal way of getting into space.
Very much so. Robert, great to hear from you. Enjoy those eclipses later this year. That'll be very exciting in Iceland if you can get there. It'll be a lot of fun too. So, Robert, hopefully we answered your question. It was an easy one, as it turns out. And that brings us to an end. Don't forget, if you've got questions for us, please send them in. We're actually quite desperately short of questions. So send them to us via our website, spacenutspodcast.com, spacenuts.io, or just do a search for Space Nuts Podcast on your favourite search engine. Click on the AMA button, that is Ask Me Anything, and send your text and audio questions in with your name and location. We would really love to hear from you. Fred, we're all done. Thank you so much. It was good fun today.
Yeah, it's been great.
It's never fun any other time, but it was good fun today.
I love connecting with our listeners, especially when they're in places like Akureyri. Yep.
Yeah. What an amazing place. See you soon, Fred.
Cheers for now.
Professor Fred Watson, astronomer at large, part of the team here at Space Nuts. And thanks to Hugh in the studio. Works really hard, but he couldn't be with us today. He got on a space elevator and he thought he'd be back in time, but some kid pushed all the buttons. So He was very angry. Anyway, he sent me a text. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.